walk in through the doors.
I was like, I've been carrying this around all year.
Thank you. All right, I got everybody's.
No, sorry. Oh, goodness. So, like, we don't have, like, we have some work that's not on this paper yet.
It's just give it to me.
I'm sorry.
It's all right.
Over those. What's on the problems with those?
All right. Well. So if you're in my physics class, I just finished grading the test from yesterday, so if you want to get it at the end of class, you can. If you know anybody who wants you to pick a test up for them in your physics class, you can text them and find out. I'll trust you. I don't think anybody's like, I'm gonna steal their physics test. I'll teach them, I'll post it on social media, disgrace them publicly. Said no one. So if you want to pick up a friend of yours test, feel free. If you check with them or whatever. Anyway, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for this course. It's drawing to a close. Help us to just use the remaining few minutes we have wisely, Lord. In your name I pray, Lord Jesus. Amen. So yes, I'm mourning the death of the course. So, and I may have heard a rumor about people wearing blue shirts today, somehow. Well, yeah, you just have to stand outside the door, listen quietly before you come back in. Simple enough. All right, so this is not quite the same as what you guys just did, right? But there is a good amount of overlap. So let's see here. Let's see. So the first one, basically, whenever I have something like this, I just multiply by r to make things, easier to understand. And then I have r squared, and then you can recognize x and y, complete the square, right? And after you, bless you, after you complete the square, then you got this here circle, and it's centered at 1 minus 1, and it has a radius of square root of 2. So if you were to parameterize this, how would you do it? You guys have had some trouble with the parameterization this semester, yeah? What would the parameterization of the circle be? Counterclockwise. X equal to... Ooh, almost, but... Oh, plus 1. Okay, I just had the one to start with, but you had it a second. Okay, fine. So square root of 2, so square root of 2 cosine t. And y was what? Yeah, -1 square root of 2 sine t, right? So when you plug those in, they will give you that equation holding true, right? And then you could limit the range of t to select subsets of the circle as desired, right? Like if you wanted the upper half, you choose 0 to pi. If you want the left half of the circle, you could choose like pi over 2 to 3 pi over 2. If you want the right half, you could choose like minus pi over 2 to pi over 2. It depends on the instructions. If you want to make it counterclockwise, or if you want to make it clockwise oriented, what do you do? Just swap out your t for minus t. There's a few other ways to do it, but All right. I don't try to memorize all that stuff. Like if I'm trying to come up with a particular, parameterization of a circle or something, I just tinker. I'll try sine and cosine. If it doesn't work, I'll try, cosine and sine, and throw in minuses until something happens like I want. Okay, so any questions about this one? So actually, I don't need all this, right? This is completely covered already by the time I get to pi. So if I'm going to set up integrals from this, I just need to go to pi if I'm not going to triple it. If I'm going to triple the integral, I can just triple up just 0 to pi over 3 because of the symmetry here, and that gives me, like, for example, the arc length. Area, let's see, area outside r equals to 3 and within the polar graph, so I'm going to, here's r out squared minus r in squared. You notice that you have to find these points of intersection to set that up, right? And that the details are on the next page. I will post this solution in Canvas once we're done here, guys. But, so that's something a lot of you were missing on the test. Like, there's probably 5 to 10 of you who, maybe 10's too much, at least 5 though, who were not clear on the formula for area in terms of polars being 1/2 r squared. Like, you were putting square roots where you were calculating area, but the square roots for the arc length, the 1/2 r squared, 1/2 r out squared minus r in squared is the way we do the area in polars. So some of you, that was like the thing that took most of your points away on test 4, right? Right. Any questions about a particular one? Let me just zoom ahead here, because we've talked a lot about, I'm going to leave the solutions that exist for the problem I gave up on. Like, I swapped that problem out for a more interesting problem for you guys, right? So I will, on my list of things to do is to solve the problems that are on your final battle that are not on this final battle, and post that as well. All right, I don't have that yet, but that is on my list of things to do today before I leave. So, like, I killed this problem. I didn't do this to you. This one here, problem 5, like, I got rid of that problem. I thought, yeah, it's not that interesting. So here's the partial fractions decomposition. What's the rule? You need to factor the denominator, right? And you should always have as many undetermined constants in the partial fraction decomposition as you have degree of the polynomial in the denominator, right? So if you've got a 4th degree, you should expect A, B, C, D, right? If I've got 4th, again, A, B, C, D. This one is just a square, so I expect just an A and a B and a C. Excuse me, just A and B. Now this one is a little bit trickier because it's what? It's an improper, so to speak, improper fraction, right? So I got to do long division before I can actually do the partial fractions. And I'd actually want to just do partial fractions on this piece. And a very common error students make is to try to do partial fractions directly on this, like set this equal to a over x plus 3 plus b over x plus 3 squared. There's just one problem with that. It's impossible. So when you do that, you'll end up writing a and b are functions of x, which is counter to the idea. Yeah.
Since b is x to the 7th on top, isn't that also improper?
Oh man, did I do that? Son of a gun. Maybe I didn't even notice it. Yes, you would. Did I not do that? Sadness.
That's plus cubic poly.
Oh. But I meant next page, apparently. Next. Wait a minute, what? Wait. Oh, it's there. Here's the cubic polynomial in question. Right here. Yep. And there's the remainder, so that would give you, a cubic divided by a quartic would be that. This divided by that would actually what you do the partial fractions to, right? All right, let's go back here. Now there, I said setup, right? So setup is different than actually computing, right? So if I just say setup, when I have more, on a final, I will typically say something like setup, and then in like bold caps, do not determine the constants in, something like that, to try to keep you from wasting an inordinate amount of time finding the values for A, B, C, and D, right? So there's 2 types of questions I'd like to ask you about partial fractions. The one is a setup question, which should take you all of about 30 seconds, right? Unless it's got the long division, then we're talking 3 minutes, right? And the other kind of problem is actually, working it out like this one. You're going to actually have to work it out. Okay, let's look ahead here. I hope I have the solution. I was just assuming these solutions are in here. Let's see here, what we got. So here, yeah, the partial fractions is somewhat simplified in that this cancels. I mean, it reduces, and then you've got just this and that, which you can find the partial fractions decomposition like so. I chose to plug in 2 and 0, and then equate the coefficient of x. There are other ways you could go here. For example, if you plugged x equals to 2i into this, it would be very enlightening. You could figure everything out from the 2i equation and the x equals 2 equations that would reveal the coefficients. Anyway, however you figure it out, here's a, b, c, you plug it back in, you do the integral. It's been a minute since we did that, right? But I hope, well, let me just say this. The final exam, like I made in the announcement, I hope you've seen the announcement. It's not a terribly long announcement, which is unusual for me, right? But I basically said what? The final exam is focused much more so on integration, like this kind of stuff, right? And also power series calculation. You know, find the first 3 terms, find the Maclaurin series, use the geometric series. That is where the lion's share of the problems are in my final. Now, it is comprehensive. There is a problem on like converge, diverge. There is a problem on parameterize this. You know, there's probably a problem on colliding tangent line. There's probably a problem, here's 2 vectors, find the angle between them. There's probably a problem on like converting from polar coordinates. There's probably a problem on calculating the area in terms of polar coordinates, right? But there are more problems on integration and power series, much more so. Because I've spent more time this semester on those 2 topics than anything else, right? So, yeah, 2 tests indeed. So it is comprehensive, but it's not, what I'm trying to get across to you is that the final exam is comprehensive, but it's not homogeneous to the course. Like I didn't do that. Now some people will be like, well, that's not fair, because that means a person can like completely fail the converge diverge test and then never really understand it and then erase that test with a higher grade on the final. Yes, I realize that. I'm at peace with it. It's not ideal, but anyway, I'm just happy if you leave the course with a above average understanding of this material. Because more often than not, in the applications of calculus going past this point, you'll find yourself either integrating or using a series calculation, or just more generally doing a like a symbolic calculation of some sort, right? That's, anyway. Well, I would hope you do that. But anyway, any questions about this? No? Let's go on. This one is a little bit sneaky. You got to make a u substitution, u equals e to the x substitution. When you do that, then you have a partial fractions waiting for you, like this. And then you can, yeah, so it's actually not that bad. This one here, if we make a hyperbolic substitution, it ends up being hyperbolic cosine squared, which we can use this identity for, and then integrate like so, and then write it like this. Of course, you could write this in terms of algebraic functions. If you're so inclined, if you go trig substitution, how's this go?
Tangent.
It's a tangent substitution. What happens to you? Derivative of tangent secant squared. This becomes the square root of a secant squared, which gives you secant. Secant times secant squared is secant cubed. So to calculate this with trig substitution, you must calculate the integral secant cubed, which is something you ought to be able to do, but you also would like to avoid it if you can. Yeah.
If you just memorize the integral secant cubed, can we just write it down?
No. If I'm asking you integral secant cube, I expect it to be derived.
But you can use partial fractions to derive it with the trig sub.
Oh, so you could derive the integral secant cube with partial fractions? This is good. You can also do that for the integral of secant, right? I don't think I ever did that this semester, but I mean, this is true. Many of the things that you previously had to rely on obscure tricks and things for, you can now use partial fractions. And I don't think I ever circled back and pointed this out to you guys, but it is true. Like, for example, integral of secant theta d theta. This is the integral, but it does require a little bit of finagling. I mean, you got to have the sense to do this. And then that is you let u equal sine theta. Then you've got integral of du over 1 minus u squared. But 1 over 1 minus u squared is 1/2 of 1 over 1 plus u minus 1 over 1 minus u. I could be wrong. Let me check on that. Maybe the other way. Maybe just plus. There we go. I think that works because if you make a common denominator, when you do this 1 minus u, 1 plus u up here, and as such, the plus minus u cancels, and it leaves you with a 2. 2 over 2 is 1, is that? And so this is actually the integral 1/2 1 over 1 plus u plus 1 over 1 minus u du, which integrates to 1/2 natural log the absolute value of 1 plus sine theta minus 1/2 natural log of 1 minus sine theta plus a constant, which is the natural log of the square root of 1 plus sine theta over 1 minus sine theta, which is the natural log of the absolute value of the secant theta plus the tangent theta after about a half-page algebra. But it's not obvious why those were equal, the last steps. But it is true. I mean, Sam is right. You can use partial fractions to do things that previously were only accessible to us through integration by parts. So if you get stuck in a corner on the final, it is a way out sometimes. It's not wrong. Yeah. Uh-oh. What'd I do? Oh, this is, if this was the sum total of what you're doing on the final or something, I would stop like back here. I mean, this would be a totally legitimate. I forgot to look. Is the camera over? Yeah, the camera's over here. This, I'm just pointing out for the purpose of connecting with what I do. Like, and to answer your question, could you memorize something? There is one thing I expect you to memorize, which is that the integral secant is secant plus tangent. I also expect you to memorize the integral of sine is minus cosine. Integral of cosine is sine. The integral of cos is sin. Integral of sin is cos. Integral of secant squared is tangent. The list goes on, right? There are many things I expect you to memorize, but like integral of secant cubed isn't one of them. Like, so. What's that? Is not. I don't expect you to memorize the derivation. I expect you to understand it. Let's see here. So this one here, the only way to integrate sine theta times cosine 3 theta is to know trigonometry. I like to know trigonometry because I know imaginary exponentials and I can do this algebra. Of course, you can also memorize appropriate adding angles formulas. If you memorize one of them, you can take derivatives to generate the rest of them, So actually, if you just memorized one of the product identities for sine cosine, you could differentiate to get all the other ones if you wanted to. I personally find it easier just to memorize that sine theta can be written in terms of imaginary exponentials and cosine can be written in terms of imaginary exponentials like that, and just do algebra. Like for me, that's the faster way to do these things. Robot apocalypse safe way of organizing these information. In my mind, where was I? So we have trigonometric substitution, we have hyperbolic substitution, I think both are important, and sometimes you just want to avoid the trig substitution. Yes, sir? Nope, that was just okay. Now the other thing, hopefully I got some more trig substitutions as we go on here, do I? Well, these are trig integrals. Well, it's unfortunate. I would say please do go back and make sure you look over some trig substitution problems where you had to write the answer in terms of the triangle. That is something I usually test on in the final. I try to make the final battle comprehensive, but sometimes it doesn't quite align with the final exactly.
What about when it's like hyperbolic? Do you know because I remember you talked about the hyperbolic triangle one time. I was so kind of confused. Like we need the hyperbolic, taking that into your x's.
Yeah, I think you do need to know that, because if I ask to, take the integral, and then I say, leave your answer in an algebraic function in as much as is possible. So for the people who chose the trigonometric route, then they could use the regular triangles. But the people who chose the hyperbolic route would want to use those other kinds of triangles. They're all basically just, it all comes back to, this though. So, but yeah, I mean, the hyperbolic triangles I introduced are ways of remembering how to, change the hyperbolic functions back into algebraic functions. That is not something I expect you to have memorized in terms of I'm trying to say here, there are formulas for the inverse hyperbolic sine, inverse hyperbolic cosine, and inverse hyperbolic tangent to rewrite them in terms of the natural log of algebraic functions. I don't really expect you guys have memorized those. I personally have to look them up every time I use them. So if that's the case for me, it's probably not reasonable for you to have to memorize those. On the other hand, I do expect you could derive those. Now, is there time to derive those on a Calc 2 final that's already busy with the marathon of material we've gone through this semester? Probably not. But that was something we did spend class time on, right? We derived like the formula for inverse hyperbolic tangent in terms of like natural log at some point. It's really pre-calculus though, truthfully told, right? You just write down y equals the inverse function and then take the hyperbolic function of it, convert it to exponentials, and then you do algebra to like solve for the thing again. But so I would say an A+ in this class looks like understanding those hyperbolic trig triangles, but you probably could make an A without knowing them. But that said, I do think that they are kind of the I think not knowing those triangles means there's some gap in your understanding of the hyperbolic substitution. I can't deny that. Could you do hyperbolic substitution without knowing the triangles? Yeah, I think so. I mean, I know so. I did it for years, right? That's a relatively recent addition to my ideas, the hyperbolic triangles. Anyway, let me stop talking about those. Problem 11. What do we do here? You want the area to be what? To be 1, right? Probability distribution has the area under it is equal to 1. So you just have to calculate those integrals and set them and choose A to make it 1. Where's my answers? So this integral is relatively easy to do. You throw away everything where it's 0, keep the places where it's non-zero, which converts this integral from minus infinity to infinity, integral from 1 to infinity. I take the limit as t goes to infinity of the antiderivative of this, which is, of course, a over pi inverse tangent. And I get 4. So let's talk about series. So you could probably ask me the question, like, which is more important, like the geometric series or the known Maclaurin expansions for sine, cosine, exponential, and cosh and sinh? And the answer to that question will be yes. They're all important. Like, I will test on all of them, right? You know this. So this guy here, it just yells at you, I'm a geometric series with c equals to x to the 6th over 8, and r is equal to x to the 7th over 8. So I use the geometric series sum there. And then remember, to find the power series expansion, we do need to clean things up, right? This wouldn't be a legit answer. I do need to like pull all the constants together so I have a clear coefficient here and a clear power like that, all right? Now, you say, well, what if I just wrote this? Well, yeah, that's a lot of partial credit for sure, but it's still not right as the power series. This one, it's not geometric yet, but we know the derivative of inverse tangent's 1 over 1 plus the input squared, right, times the derivative of the inside function, chain rule. So it gives us this. And that is geometric. We apply the geometric series. In this case, the c is 3x squared, and the r is minus x to the 6th. I took the liberty of pulling the -1 to the n out in my initial step, and then cleaning things up, we get that. Now that's not the answer, of course, because we're trying to find the power series for f, not df dx. So we have to do what? Integrate term by term. Now it just so happens the constant here is 0, but sometimes I work very hard on the test to make sure my constant's non-zero to see if you're checking. This has happened to you in the semester already. Yeah.
For like tangent inverse, if you memorize the power series, can you just plug the x to the third into the power series?
If the problem is about deriving, if the problem says use geometric series techniques to find the power series expansion for inverse tangent, then I want you to use geometric series techniques to. But in the wild, if I just say find the Maclaurin expansion for inverse tangent and you happen to have it memorized, I can't take that from you. You can use it, of course, yeah. So that depends on instructions. Generally speaking, I'm happy if people have the right answers here. They can't. But if I say use geometric series techniques, I really do mean that, and I will not be very happy if you spend a half hour of your final exam calculating derivatives to arbitrary order to find a pattern and use Taylor's theorem. Like, I will be very annoyed, actually. Because then what will happen is the rest of your test will have didn't have time, didn't have time, didn't have time. It's like, you had time, you used it unwisely. You had all the time you needed before you did that. But anyway, I know. It is true, nevertheless, that you didn't have time when you wrote I didn't have time. Like, you're not being dishonest. It's true. Anyway. One of Dr. Skambordis' pet peeves is when students say that they're confused. He gets so angry about students saying they're confused. I was like, but they are. Like, I don't know. So, and I know in the same vein, you did run out of time, and I'm just upset because it didn't have to be that way, right? I mean, if you okay, so anyway. That's just a general point of order in terms of test-taking strategy. Like, as you're spending, 30 minutes on a problem, is that wise? Like, is that what you should be doing? Because there's, like 20 problems or 24 problems or whatever on the exam. So yeah, 2 hours. How long should a typical problem take you? Like, not that long, right? Now, some might. There might be some problems in there that take 20 minutes, and we all get stuck on things, right? Like, I know I spent 20 minutes staring into space once in an hour test. Like, I just didn't know what to do. And all of a sudden it hit me. What are you doing? Start writing stuff. You idiot. So it turned out okay, but it was kind of borderline. The thing that was aggravating is the problem I was stuck on. I'd studied, I knew the answer to, and here I am, 30 years later, it still bugs me. But 20 years, I don't know, however old I am. Any questions about this one? So yeah, integrate to get back. You gotta check the constant by plugging in 0. When I plug a 0 in, this is the 0 series. So the constant also has to be 0 since inverse tangent of 0 is 0. But if the function you're working with has f of 0 not being 0, and or there's a constant here, beware, it doesn't always have to be 0, all right? So like, I think on your test in the semester it wasn't 0, right? Yeah.
But you can just plug in 0 to find the constant.
Yes, yeah, we can plug in 0 or
The extra goes to 0.
right, or if the series was centered at some other point, I would plug in the center point to fix the constant. Because plugging in the center of the series will kill everything except for the constant term. So find the first 3 terms. By and large, you want to use substitution techniques here. It is, on rare occasions, appropriate to differentiate, but it's really not that difficult to come up with problems where finding the first 3 terms requires you to do something like 20 derivatives, right? So relying on Taylor's theorem to find the first 3 terms is not a safe method. It's just not, right? You need to use the substitution ideas, multiplication of series, division of series, to do these kinds of problems, generally speaking. All right, let me kind of, and then, I don't know, like, so, and admittedly, this problem here, up here we have the Taylor's theorem way, right? You happy?
Always happy.
Okay, that's good. So this is Taylor's way. And Taylor's way is a good way here. right? Because taking derivatives of this function is fruitful. It's not too hard, right? And when you look at 1, these are not all 0, right? If you're taking derivatives and every time you plug the center point in, you're getting 0 repeatedly, probably you shouldn't be trying to use direct application of Taylor's theorem, right? But this one you can, and it's actually pretty fast to come up with that. So I would say here, arguably, my other stupid add 0 method is probably not the best method. But here's how it goes. If I, replace x with x minus 1 plus 1, that creates an x minus 1. And then I just multiply this right here by laws of exponents as e to the 2x minus 1 times e to the 5. So then I use the Maclaurin expansion for the exponential to get that. And then this x minus 1 goes to here. This 1 is just this term over here. And then I just collect things order by order, going from constants to linears to quadratics and so forth. I would say that you really do need to have the binomial series. I forget to mention that, but I do expect you know the binomial series. Not the totality of it, but like the first about 3 or maybe 4 terms probably. Just enough so that you know the pattern, which is what? 1 plus, how's it go? 1 plus alpha x plus 1/2 of alpha times alpha minus 1 plus 1 over 3 factorial of alpha times alpha minus 1 times alpha minus 2, and so forth and so on. Of course, times what? Times the u, and then the u squared. And my point to you is just know the first few terms in the binomial series. We've used it a bunch of times, and it's easy enough to use. It's very nice. It's actually very, very nice for this kind of problem, right? Because if you were to do Taylor's theorem directly, I'd have to calculate 8 derivatives of this thing to get out to here. You don't want to do that, right? I mean, that would be, yeah, it would be stinky. And not in the hilarious way my boys enjoy. Let's see here. So let's see here. Let me skip ahead a bit. So you've got your, it's easy enough for me to ask a question about radius of convergence and interval of convergence. The thing you should have learned is that, every power series has a center. Every power series has a radius, right? And so there's a clearly defined radius of convergence, an interval of convergence. And so we had that question which was based on like, if you have a point of divergence or point of convergence, what's the largest or smallest interval of convergence? That's a really nice problem for the final because it doesn't require a great amount of calculation. It's just totally conceptual, right? That's a very nice test problem. This is not a power series. Why? Because we don't have x minus something. We have 2x minus something, right? And so if I rewrite that as x minus something, it gets this. And so there you go. There's the power series. And from this, we can manifestly see that we're looking at a power series centered at 3/2. And these are the coefficients. And if I wanted to calculate the derivatives of the function at 3/2, I could equate this to the nth derivative at 3/2 divided by n factorial. I could easily figure out what's the 100th derivative of this function, all right, by looking at this and equating it to the term from Taylor's series. So let's see here, briefly. Why does this converge? I look at it, I go, well, k and k cubed are dominant. This is essentially the p equals half series. It's the tail of the p equals, why did I say half? P equals 2 series, dummy. Me, not you. So this is a p equals 2 series, so it's going to converge. If you want to prove it, limit comparison is a nice choice. This one is an alternating series. It's got a denominator which is getting huge, so it goes to 0. 1 over that goes to 0, so it's an alternating series. It converges, right? This one down here as, this one down here, basically this is like a 1 over n with a 3, and this cosine is just going between plus or minus 1, right? So this smells like the harmonic series, right? It stinks. So that thing's probably going to diverge. I think you can use a direct comparison test there. Hopefully by now you have got it out of your system. The limit as j goes to infinity of inverse tangent of j squared plus 3 is equal to pi over 2. this term, the jth term in this sequence, converges to pi over 2. Therefore, the series diverges. Because there's a distinction between where the limit of the term that you're adding versus the limit of the sequence of partial sums, which is the series, right? So by the jth term test or the nth term test here, this diverges. Because that term converges to something non-zero. Now, if that goes to 0, that doesn't prove it converges, right? There is no jth term test for convergence. There's only divergence from looking just directly at the limit of the jth term or the nth term in the sequence. That is the fundamental confusion that everybody has to get past at the start of all this. So this is a kind of sneaky thing. This was essentially our proof of the nth term test. We looked at the difference of the partial sums and saw that it was equal to the kth term. And so if you have a formula, you can figure out what the kth term is. All right, then we had differential equations, which is kind of, what do we learn in differential equations? Essentially just what? Separate, integrate, right? And then what else? Integrating factor method if it's a linear problem, right? There's something new that's brought to the table, though. Now you guys know about power series, right? So if you can't do the integral with our previous means, now you can use power series to calculate the integral. That was problem 19 on this, right? Point of order, if you see inverse function, how do you do the integral? Integrate by parts, right? You see cosine to the fourth, how do you do the integral? You've got to do trigonometry, right? You got to split it, apply double angle twice. You got to deal with it. So this one was integrating factor, and it just so happens that it lands you to something that you can't integrate with conventional non-power series methods, but with power series, it's a piece of cake. There it is. So, well, it's been fun this semester. I want to tell you guys a couple things. Number one, you've been a great class. Number two, if I'm going to try to look at like the double major in, I want to look at the double major in like math and electrical engineering, see what it involves, or just more generally engineering, because I don't think we've really provided a document for you guys that just kind of maps out what a double major in math and engineering would look like. I mean, everybody knows about the minor. That's easy enough, right? You take a course, right? But I think we do have a pretty good math department here, and some of you, especially if you're, graduate school bound in engineering, you'd do well to take a few more math courses than engineering requires of you. Just saying. There's something else I was going to tell you. Yeah. Oh, no. Oh, the other thing is, if you're looking for a way to save yourself time in your schedule, I have a couple of things that I shouldn't tell you about, but I'll tell you about. Number one, you could ICE physics. If you have physics like 231, institutional credit by examination. Now this requires self-motivation. If you work physics out over the summer, you can take a test. If you make like over 70% on the test, then you've passed this ICE exam, which is essentially a final exam from some past year sometime, right? So if you have the determination and the willpower to do it for yourself, that could save you taking physics, which is a huge time sink in the semester, right? And similar options exist with like Calculus 3. But of course, I'd be happy if you come take my Calculus 3 at 8:15 Monday, Tuesday, Wednesday, Thursday, and Friday.
Like soap on Saturday.
Yeah.